Absolutely. Okay, so I feel like this is really loud today. I'm gonna move it a little bit. There we go. Okay, so as promised last time, I paid attention to what Dr. West was doing in class, and there were a couple notes we had to fill in for the gem-diol reaction. So we're gonna do that first, and then we're gonna move on. So for the gem-diol reaction, well, in all of the chapter 16 reactions, we talked about how they are reversible, right? And that means we're going back and forth between the product and the starting material. So specifically for the gem-diol reaction, we have to pay attention to where the equilibrium is pointing, aka which side of the equation we're favoring. So in the gem-diol reaction, we could either use an aldehyde or we could use a ketone, and then we could use acid catalyst or base catalyst. And this is the mechanism, but I'm gonna go ahead and zoom in just a tad. And we are going to go up here, and we're gonna do kind of like a summary, right? So if we have a ketone and H2O and acid or base, we're gonna form a gem-diol. And I know you guys talked about this in class last time. So what's more favorable, a ketone or a gem-diol? A ketone, and why is that? There's a couple of reasons. So yes, so the carbonyl carbon is sp2 versus here it's what? sp3, cool. So for this arrow, I'm gonna draw the longer arrow pointing towards the ketone and the shorter arrow pointing towards the gem-diol. And all this means is that this reaction is going to prefer the ketone to the gem-diol. Now, if we do the same thing with an aldehyde, our equilibrium arrow is going to be a little bit different, because now Dr. West mentioned something important about aldehydes that are different than ketones. Yes. Good question. So the way the orbitals are like oriented in sp2, it tends to be a little bit more stable than sp3. Also because this double bond helps to stabilize all the electrons that are happening. Something you don't have to know necessarily, but there's an effect called hyperconjugation. Yeah, that happens when it's sp2. So all of those things plus resonance help stabilize sp2. Very good question. All right, so I'm just going to fill in the reagents again. H2O, acid or base. Don't yawn, I'm interesting, I promise. Okay, so what is it going to prefer for the aldehyde? The product, exactly. And so the reason for this is because the aldehyde is super duper reactive because of sterics. It's less sterically hindered than the ketone, and electronics. So there's less donating groups, which means this is a stronger delta plus. So sterics, less steric hindrance, electronics, less electron donation. That's why it's more reactive. Yes. He mentioned a little bit of acid versus base stuff, but it gets a little bit complicated. So yes, he did say that acid catalysts are going to prefer gem-diols more than a base catalyst will, but I think the overall thing he wanted you to know more so was that ketones are more stable than aldehydes. So ketones will prefer the ketone form, and then aldehydes prefer the gem diol form. But yes, definitely in the PowerPoint slides, it mentions how like acids for certain reasons are going to prefer the gem diol versus bases are going to prefer the ketone or aldehyde form, but that's a little bit less important than the other effect. Yes. Say again. I mean, the intermediate is going to be more positive. So like we saw over here, and you know what, this kind of answers both of your questions, so I might as well show it to you. So for the gem diol thing, when we have an acid catalyst, we get a positively charged intermediate, right? Positively charged, and then we get the gem diol. Versus here, we get negatively charged intermediate, negatively charged gem diol. So between these two intermediates, which one do you think is more reactive? The top one or the bottom one? The top one, yes, because this H makes this a more electrophilic electrophile. Whereas this one only affects the nucleophile. So this reaction is more likely to happen. And that's why in an acid catalyst, it's more likely to move onward because the electrophile is made better. But yes, so to answer your question, Eric, the intermediate definitely is more acidic. It's more plus charged, but the final product and the starting material are ultimately going to be the same in both cases. Make sense-ish? Okay, cool. Yes. Good question. So you're basically asking, like, is this the intermediate or is this both the intermediate kind of thing? So technically, there's no well-defined intermediate in this reaction, but the, like, kind of the definition of an intermediate would be one single molecule. So it wouldn't be this step necessarily. It would just be this molecule or this molecule. That's a really good question, and that's more like an Orgo 1 thing where they would ask you about the arrows. The only ones he's going to ask you for an intermediate on is probably going to be acetal and ketol, because this one has a well-defined intermediate that has its own name and everything. So he could ask you, like, in a reaction of acetal with, or not acetal, or acetal with base and H2O or something like that. What would be the intermediate? And you would be expected to know this guy would be the intermediate. Very good questions today. So how are we feeling with acetal-ketol reaction and gem diol reaction? Good, bad, in the middle? Okay. So the next, or before we move on, I did the summary for the first one, so I might as well do the second one. So for the acetal-ketol reaction, we're going to start with a ketone or an aldehyde. And equilibrium is pretty much going to be equal for this one. We're going to react with an alcohol. And if we react with a base, where do we end? The hemi, yes, exactly. And so the hemi is going to be one OH group and one OR group. And then if we had a, let's do an aldehyde just for fun. So if we had an aldehyde, again, if we had an alcohol present, and this time if we had acid present, what are we going to form? Acetal, yes. The reason it wouldn't be a hemi is because we're going to go all the way to the final product. So it does form the hemi in between the steps, but it doesn't stop there. So the best answer would be acetal. And so what are the two groups coming off of the acetal. 2 OR groups, absolutely. Cool. All right, you guys seem like rock stars for the stuff we did last time. Yay. Yes. Okay, great. So let's scroll down to this naming stuff. So there's a whole list of molecules that we're going to name eventually once we're done with all the reactions. But I want to focus on this last row right here because those are all acetal ketol stuff. So when you're naming these, what I want you to do is first look at these two groups, right? If we have an R and an H, we know that had the aldehyde base, right? So we're going to call that an acetal. And same exact thing here, acetal. Yes, that's what I was getting to next. No, that is completely okay. That was a good segue. So how did you know that one was a hemi versus the other one was not? Yes, so one of them has an OH and the other one is an OR versus the second one is 2 OR groups. So this guy is just an acetal because there's 2 ORs. This one is going to be a hemi acetal because there's an OH present. So then when we're talking about ketols, it's going to be the same exact idea, except now instead of an an R and an H, we get 2 R groups. So if you see 2 R groups, you can think of that as like a ketone base. And so we're going to call them both ketols. And then left or right, which one is going to be the hemiketol? The left, because it has an OH present. Perfect. All right. I said all right like 100 times. There you go. Does this answer your question a bit? Cool. You're very welcome. All righty. Any other questions? Okay, cool. So we're going to move on and we're going to do another mechanism now. And I know the mechanisms are kind of scary, but I promise we'll do it slowly and we'll do it together. And again, if I'm going too fast or if you need me to slow down and answer a question at any point, please do not feel afraid to ask. That was a mouthful. I don't know why that was so hard to say. So the next reaction we're going to do is the imine reaction. And the key that you have to look for in the imine reaction is, hold on, I said that too early. The nucleophile, it has an N, and it's going to have 1 R group and 2 hydrogens. So can anyone tell me, what is the name of this functional group? Primary amine, yay! Cool. All right, so it's primary because there's only 1 R group attached. And for this one, it's great because acid and base doesn't really matter and aldehyde and ketone doesn't really matter. So you're going to get the same product no matter what combo you use. So just for funsies, let's use an acid. And acids are going to make... Yay! Okay, so we're all going to say it one more time. Acids are going to make... Wonderful, wonderful, wonderful. I could see in lecture when Dr. West was like saying that last time, everyone was like, we get it, we get it. And I was like, yeah, you guys are already getting sick of it. I love it. All right, so electrophiles are going to become more electrophilic. So what does that mean? What's the first step here going to be? Protonation. What are we protonating? The oxygen. Yay. All right. So the first step here, we're going to protonate, which means the oxygen is going to steal a hydrogen, give those electrons back to the carbon, the chlorine, and we get O with an H on it. And so what charge do we get? A plus charge. Sorry, my pencil is being weird. There we go. Plus charge. So what do we have left over in solution? Cl minus, yes. And we also have our nucleophile, which hasn't changed yet. So we're going to draw it exactly the same as it was before. So just so I know we're clear, what exactly is the nucleophile here? The nitrogen. Perfect. So the whole amine is the nucleophile, but specifically the thing doing the attacking is the nitrogen. Cool. So the nitrogen is going to attack the carbonyl carbon. Those electrons get knocked up to the oxygen. And I'm going to zoom out just a tad and scoot over. So what happens to the hybridization of that carbonyl carbon? It goes to sp3. Cool. So it's sp2 here, sp3 here. Awesome. And now we have added a bond to nitrogen. And then nitrogen is attached to so many things. Bam. So how do we feel about this guy? Nitrogen is positive. Exactly. So how many bonds does nitrogen want to be happy? 3. Awesome. So 4 is way too many. It wants to get rid of one of those bonds. So what's the easiest way to get rid of a plus charge? Deprotonate. Cool. So what do we have left in solution that could deprotonate? Cl minus. Perfect. All right. So Cl minus is going to deprotonate. That means it's going to steal that hydrogen, bring those electrons back to the nitrogen. And hello, assistant. Okay. So now we have one R group, one H group. Not like we're in the middle of something or anything. Yes, what's up? Wonderful question. So the intramolecular proton transfer is kind of like a cheat that chemists use so they don't have to draw a million steps. So I'm actually going to show you that once we do like the longer mechanism, then I'll show you like the shortcut. It could happen, yep. So what would happen if we did the intramolecular proton transfer? Perfect, yes. So I will show you how that works. I just want to draw out like the whole thing so people don't like get confused or anything. All right, so now, are we happy? Is there anything else we can do here? Kick out the leaving group, cool. But what do we want to do? Like, is OH a wonderful leaving group the way it is here? No. So what can we do to make it a better leaving group? Protonate it. Awesome. And what could we use to protonate it? HCl. Perfect. So the O is going to use one of its lone pairs to steal a hydrogen, give those electrons back to the chlorine. And now if we add an H, sorry, I'm having trouble fitting the whole thing on the screen, but. All right, if we add another H to the oxygen, what charge do we give it? A plus charge, yay. So by giving it a plus charge, we made it an even better leaving group, which is what you guys told me before. And how do we make a leaving group leave? Yes, okay, so putting together a couple of things you guys said, the lone pair from the nitrogen is going to drop down and make a double bond. So we go bam, and this causes this to be kicked off. And we get boop, boop. I'm going to get tired of drawing these equilibrium arrows very soon. I can feel it. Okay. So now this nitrogen is attached to one hydrogen and one R group. What? And that's why they're called substitutions. Yes. Great question. So let's just finish this one last step and then I will show you exactly what that means. What do we do for this last step? What do you guys think? First of all, what's wrong with this? The nitrogen has a positive charge. Yay! And to whoever was mumbling, I promise I'm not targeting you especially. I just like making fun of people. Was that you, Leah? So sorry. Okay, so how can we get rid of that plus charge? What are we going to do? Get rid of the hydrogen. I thought you said give it a hydrogen. I was like, no. And someone asked a very, very good question, which was, where are we getting all of these HCl's from, right? That is so valid because, like, what the heck, right? So that's a two-parter. One, you're in a solution of HCl. So you can assume there's as many as you need. But also, if you keep track from the beginning of the reaction, we start with HCl, we deprotonate it, we get Cl minus. We protonate it, we get HCl. We deprotonate it, we get Cl minus. And now we still have some Cl minus in solution, and that molecule of Cl minus is what will do the deprotonation. Cool? Yes. Yes, we will have H2O. It's just not super important because it can't really deprotonate. Alrighty, so the Cl minus steals the hydrogen, yay. And we get our lovely final product in 57 steps with a lone pair. Cool. And what is this lovely thing called? Yes, the imine or the imine or whatever you guys want to pronounce it. Dr. West says it in the loveliest way with his accent. I'm not going to try to recreate it, but you all know what I mean. Imine. 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 I just love his accent. It's adorable. Okay. Imine. Okay. Anyway, I said I'm not going to say it, and then I said it like 12 times. Yes. Okay, good question. So the reason it's not going to be the first step is because of the HCl. Disclaimer. I'm going to do a little asterisk, a little disclaimer that nobody listens to. If you do any more chemistry in the future, you will learn that a lot of the stuff I'm telling you is straight up a lie. Chemistry doesn't really work like this. If you put a molecule into a solution, it's just going to bounce around and do whatever it wants. It's not going to be pretty and organized. But for the purposes of this class, we're going to pretend that chemistry is really structured and really orderly. And conceptually, we know that an acid catalyst, the whole point of it is to protonate and make things more electrophilic. So when we draw this reaction, we're going to do like a prepping step almost, where we protonate the carbonyl, make it more electrophilic, and then we attack. That was a really long-winded answer, but does that sort of kind of make sense? Yeah. Because of the acid, but also don't hate me when you find out this doesn't actually happen. Yes. That's a wonderful question. No. So the best part of these reactions are I give you the whole thing because you need to understand it conceptually, right? But after we do the whole thing, we're going to do a summary, and the summary is all you're expected to do. So this is the whole thing. Take a picture, take a note, what else? And then the summary would be...
So wait, you're teaching them something that doesn't actually happen and at the same time is also incorrect.
You know what? I didn't ask for the sass. But yes. It's just science. Yeah, like I was upset about it too, don't worry. I was sitting in advanced orgo and I was like, so you're telling me everything I've done is a lie? And he was like, yeah. And I was like, okay. And essentially, I'm not going to say this to you guys because I'm not mean, but the professor was basically like, yeah, your tiny little sophomore brains can't handle real chemistry. And I was like, whoa. Okay, there we go. It wasn't properly screwed in. Okay. So we're going to say NH2 and an R group, and we're going to say acid or base. And this goes back to your question, which I forgot to answer. So in an acidic solution, we have like HCl, HI, HBr, any of those acids. In a basic solution, we're going to say NaOH, NaI, NaCl, any of those bases. So plus charge equals acid, minus charge equals base. Okay, so we're going to say acid or base. And all I want you to know is that we take the O, we swap it for a nitrogen, and all we keep is the R group. We magically get rid of the hydrogens. Yeah. That's it. Yep. And everyone's like, why'd you waste 15 minutes of my life? I know, you have to know it. I promise. You have to at least see it once so you kind of sort of know what you're talking about. Before the exam, I really don't want to see anyone like fervently like writing all of this down. I promise. It's not, you don't have to draw every single step. Yes, so that one was this. Yep. Okay, do you want to start throwing the candy at people?
Yes.
Okay, so every time I ask a question, when someone gets it, just give them some candy.
Just give me a target.
Well, you have to walk around. Come on, go.
I got range.
No, you can't hit my students. Just shush. I do not. Okay, yes, what's up? Exactly. So yes, if we had a base, the first step would be that we deprotonate this nitrogen and we give it a negative charge. And then if you want to see like the whole thing, I can show it to you after the session. Okay. Yes. Oh, okay. All right. So, yes. Yes, so that's a good point. If we did this with an aldehyde, the only thing that changes is we get an H here at the end. I sensed a hiccup coming, but it didn't happen, so. Okay, any more questions? You guys are asking such great questions. I love it when you guys are interactive. Gives me all the serotonin. Yes. Yes, so I didn't say this explicitly, which is my bad, but let me go back up here. These are all basically the summaries. If I could work my iPad, that would be lovely. Ta-da. Okay, so we are going to go on to the next one, which is the hydrazone reaction. And again, this is going to be a ketone or an aldehyde, and it's going to react an acid and base. And just because I like HCl, we're going to stick to HCl. Does anyone know what the nucleophile looks like in this reaction? Yay! Oh my gosh, don't do that again. Okay, I'm gonna have to revoke your candy powers. Nope, 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 nope.
One more try. One more try.
There we go. All right.
You just didn't catch it.
Anyways, so what is this reagent called? Oh, we got a 50-50. Some people said hydrazine. Some people said hydrazone. We're going to put a pin in it and come back after we draw the product, and you'll see why. Okay. So what's the nucleophile in this reaction? The nucleophile. Yes, the NH2. So specifically the N. Go ahead.
I don't know who said it though.
Okay. You know what? You don't have to be picky, bro. Like, kidding. You spiked it. You didn't. You were like, no. Anyways, you know, I don't know what it is with you guys today, but you're like laughing at my jokes. You're answering questions. I should wear the horns more often. All right. So yes, the nucleophile is going to be specifically the nitrogen. Does it matter which nitrogen? No, why not? They're exactly the same. Cool. The reason I bring that up to everyone. So the reason I bring that up is because there is a reaction where they are not the same. We'll talk about that when we get to it though. So if we have an acid catalyst, what's the first step? Protonate the carbonyl. Cool. You are not going to reach all the way back there.
Maybe.
Everyone's like, absolutely not. I'm not going to get hit in the face with chocolate. Bro, you need to walk to them. No, you have to walk to them. You're going to get your privileges revoked.
At least half that.
No, you get negative credit. All right, so after we protonate, what's left in solution? Cl minus, cool. And then we have our nucleophile. So I'm going to draw it like slightly more open so that we could see everything going on. So the lone pair is going to attack here. Bring those electrons up. And we get OH. And we also get N, NH2, H, H. So what charge does the nitrogen have? Positive, cool. Now throw it. Cool. So what were you saying before about? Yes, so where would the proton go from and to? Perfect. So the intramolecular proton transfer, I'm going to do it in blue. The intramolecular proton transfer is basically when we take a proton from one of the heteroatoms onto another one. And so essentially, this is one of those things where does it actually happen like this? Does it actually happen in two steps? What's the truth? This is something that different professors debate on, right? So when I was taking this class, Dr. West said it really does happen like this. And then my TA in Orgo Lab told me it doesn't happen like that. So it's one of those things that every professor has their own opinion on. So for the purposes of this lecture, we're going to say that the hydrogen could either go in two steps or it could do the intramolecular proton transfer. This is just easier to draw. So this is what professors usually draw out instead of drawing all the little steps. Question? So not always. It could be any acid or any base, but I just prefer to have it like consistent, so I use HCl. Well, any Lewis acid. Yeah. Because you need a proton. Alrighty, so once we do our little proton transfer, what's the charge on the oxygen going to be? Positive. Yay. And so we made it a what? Oh, yes, you can't see that. We made it a better leaving group, perfect. And now the nitrogen no longer has a charge. It just has one H and one NH2 and a lone pair. So the next step would be getting rid of the leaving group. How do we do that? Yes, so a couple of you said it. So the lone pair is going to reform the double bond, and we're going to kick off the leaving group. So bam, bam. And we get, sorry, I'm trying to make it so you guys can see it. I don't know why this screen keeps like doing what it's doing. So we get a double bond to a nitrogen. The only difference from the imine is that now the nitrogen is not attached to an R group, it's attached to an NH2 and a hydrogen. So are we satisfied? No, why not? Too many bonds, yes. So we have a plus. And then some of you guys already answered the next question. Cl minus, yes, is going to come in and deprotonate. So Cl minus is going to steal the extra hydrogen. Bam. And now we get our lovely final product. Yes. Yes. Okay, so let's name this one, and then we'll go back to your question, because it builds on each other. Yes. Yes. Good question. And that's what we did in like the acetal reaction, right? So the only reason we can't do that, so in case anyone didn't hear him, is it possible instead of just like deprotonating and whatnot, reattacking with another molecule of the hydrazine? No. And we're going to say that's because there's too much steric hindrance. So if you have the option of stealing a hydrogen, that's what you're going to do, because sterics are really annoying. All right. So this is one of my favorite parts of this chapter, because I love to make this dumb pun. Okay. So we have the hydrazone. That name is already given. So the hydrazone is the name of this product. And then someone already mentioned it, but I'm going to pretend they didn't. The name of the reactant is hydrazine. And I know what you're all thinking is, wow, how do we know which one is a hydrazine and which one is a hydrazone? Well, don't worry, friends. I have a wonderful way to remember it. Okay, so the hydrazine goes into the reaction. Everyone's bracing themselves like, what is she going to say? And then the hydrazone comes out of the reaction. Or how I choose to remember it, hydrazone, snap, it's done. I'm telling you, dude, you're annoyed by it. But on the exam, you're going to sit there and you're going to be like, oh, it's the question's going to be like, which of the following is a hydrazone? You're going to be like, oh, dude, I don't know. And then you're going to hear, oh, snap, it's done. And you're going to know. Or not, but it's fine. Yes. Yep, if it's an aldehyde, you just add an H, but the naming would be the same. Okay. I see a couple hands, but one second. Back to your question. We're going to go up. Just kidding. We're going to go down right here. So we have our hydrazine and our hydrazone. And the question he asked me before was, in lecture, Dr. West drew like some weird thing coming off of this. And there's only going to be one specific reaction that has something coming off of the hydrazine. And that's going to be specifically this guy. And this guy is phenylhydrazine. And what do you think the phenylhydrazine could possibly make? Phenylhydrazone, yay! And that looks like this. Don't maim anyone. Ta-da! And I wanted to do a quick review game at the end, but I don't think we're going to have time for that, so I'll save it for the next session. Instead, we'll just name this together. So we haven't done these two yet, so I'm going to save that for next time. But what is this guy called? A gem diol. That's okay. If you all get it right, you all suffer. What about this guy? Whee.
And which one?
The imine. And then what is this called? This one on top. Primary amine, yay. And then this one isn't drawn in your packet, but I'm going to draw it for you anyway. So what if we have N with 2 R groups and 1 H? Secondary amine, yay. Ta-da. So let me zoom out so we can look at it. And just 1 minute quick summary. So electrophiles, oh darn it. Acid catalysts do what to a reaction? They make the electrophile more electrophilic. Okay, what do bases do? Make the nucleophile more nucleophilic. Cool. So primary amine plus a ketone, what does that make? The imine, cool. In the hydrazone formation reaction, what is the nucleophile? Hydrazine, yay. What was your question? I saw your hand. Hydrazine is just NH2, NH2. Hydrazone has the like double bond. Great question. All righty. Well, with that, I'm going to let you go. Have a wonderful Wednesday, and I will see you guys on Friday. And I'll be here if you have any questions, as always.